Okay, welcome back, everyone. And we will now be hearing a categorical proof of the Carathéodory extension theorem from Ruben Van Belle. Thanks, Ruben.
Yeah, thank you. And thank you to the organizers for organizing this. So yeah, I will say something behind the category theory of the Carathéodory extension theorem. So yeah, I'll start maybe by saying what the Carathéodory extension theorem is. So it's a resulting measure theory. So it's quite an important resulting measure theory because it proves the existence of things like the Lebesgue measure or Brownian motions and things like that. And what it says that we can, if we have a pre-measure on an algebra of subsets, so that's closed under unions and complements. If we have some sigma additive map rho like this, then we can extend that to the sigma algebra generated by those sets to an actual measure. And that's very useful because a lot of sigma algebras we want to work with are of this form. But the classical proof is quite complicated, or it's in a lot of steps and a lot of things are going on. So kind of a diagram of what's happening in the classical proof is that we start with this pre-measure rho, then we extend it a bit more to something sigma additive, then we extend it to the whole power set to an outer measure, so that's sigma sub additive. Then we restrict it to something sigma additive, restrict it even more, then extend it back, and then in the end we have the extension. So there's a lot of things happening. So the goal I had was to find a more structured approach using category theory to see what's actually going on and to have maybe a bit more intuition of how things work. So that's the Carathéodory extension theorem. Another thing I was interested in were joints of measures. So if you have a directed collection of measures, then the join or the supremum is given by the obvious thing. So you take pointwise suprema, and that turns out then to be a measure. That's not too difficult to show. But if you have just two measures and you take the join of those, then you get a more complicated formula. So then there's some other operation going on, taking this supremum over all these partitions. And I also sort of want to figure out what the category theory behind this formula is. So where does this come from categorically? So to do that, I wanted to work with Lax transformations and categories of Lax transformations. So that's the first thing I'm going to say something about, and then I'm going to say how that relates to measure theory. So why I wanted to work with those. Then in the second part, I'm going to say something about the co-limits in these categories. And these then will tell us something about the suprema of measures and all their variations. And then in the last part, I wanted to look at extensions of Lax natural transformations. And that will then finally give us the Carathéodory extension theorem. So yeah, that's the plan. So for the first part, these categories of Lax natural transformations. So I fix a category C and some two functors H and G from C to cat. I also fix a collection of morphisms in C. And then I'm going to look at sigma Lax transformation. So a sigma Lax transformation is a Lax transformation from H to G such that the two cells sigma F are isomorphisms for every F in this fixed collection. So that's, this is some notation. So then this the category of these sigma Lax transformations and the modifications between them. I use this notation for that. And then we have inclusion functors. So we have yeah, the pseudo-natural transformations are all sigma lax, and every sigma lax is lax. So yeah, these are the categories of lax transformations I'm interested in. So now the reason why I'm interested in those, why I want to work with those to say something about measure theory, is because I can represent measures as these lax transformations. So to do that, we need two functors. So I'm going to describe a first functor with the domain, the set category of countable sets. And I'm going to send every countable set to this poset or category if you want. So that's with the pointwise order. And I'm going to use notation GA for that. Then for every countable set, map of countable sets, we get an order preserving map like this by summing over the pre-images. So that gives us one functor. Then for the second functor, I'm first going to look at this inclusion. So every countable set induces a measurable space by just giving it the whole power set as sigma algebra. And then I'm going to fix a measurable space X, and I'm going to look at this functor. So it sends every countable set to all the set really of measurable maps from X to A. And I view that as a discrete category. So how can we think about this set or this discrete category? It's all the A-indexed measurable partitions of X. And then using that identification, we can say what this functor does on maps as well. So it sends an A-indexed partition to a B-indexed partition by this, by taking the unions over these pre-images. So yeah, that's the second functor. Then first, yeah, some more notation. So I'm interested in the measures, and I'm going to use this notation for the posets of all measures where the order is given pointwise. And then, yeah, the representation or the identification is as follows. The pseudo-natural transformations from Fs to G correspond exactly to these measures. And I guess the intuition behind that is this Fs functor had information of the measurable subsets, and this G were real values, and then the naturality condition gives us this sigma additivity. So that's a first example. Then I also want to use outer measures. So an outer measure is a sigma subadditive set function. So we have an inequality instead of an equality in the sigma additivity condition. And to represent those kind of measures, I'm going to use the category of countable sets and partial functions between those. And I'm also going to use the category of measurable spaces and partial measurable functions. And then in a very similar way as before, as in the other example, we have a functor G defined by this, and a second functor like this. And the second functor, again, we can identify or that gives information about countable pairwise disjoints measurable sets, or countable collections of the pairwise disjoint sets. Then I'm going to use M out X for the poset of outer measures. So that's notation. And now I'm going to use this sigma. And this sigma is going to be the collection of all injective morphisms in this category. And then the representation results is as follows. The pseudo-natural transformations between these functors are the measures, and the sigma lax natural transformations are the outer measures. So yeah, the laxness gives us these inequalities, the sigma sub-additivity. And then a final example is, well, really very similar to the previous things. We can also do something for pre-measures. But yeah, there's a slightly more complicated, or there's a little extra thing that I'm not going to say more about, but it's essentially a very similar as the two other representations. So pre-measures are also some kind of transformation between functors. Okay, so what do we have so far then? We have now measures and pre-measures are pseudo-natural transformations, and outer measures are sigma lax natural transformations. So then for the second part, I want to say something about the co-limits in these categories of transformations. And for a first result is about co-limits of lax natural transformations. So if we assume that GA has co-limits of shape I for all A, and that GF preserves those co-limits for all F in this fixed collection sigma, then the category of sigma lax transformations has co-limits of this shape. And we can say even more, we can say how they are constructed. They're constructed point-wise. So in the most obvious way, you would probably guess that's how these co-limits look like. But yeah, in general, there's more co-limits that aren't maybe not constructed like that, but still exist. So we are also going to look at those kind of co-limits. And the approach we're going to take is we're going to look at situations where this inclusion functor is reflective, so that we can turn any sigma lax transformation into a pseudo natural transformation in a universal way. And to do that, I'm going to try to construct the actual reflector. And to construct that, we're going to need something else. So there's this inclusion functor of functors into lax functors, and that has a left adjoint. So that's explained in this paper. So this left adjoint, I'll denote by this hash notation. And then the adjunction gives us a correspondence between lax transformations and pseudo transformations like this. Then just by the adjunction, we have a pseudo natural transformation like this. And then purely notation wise, I'm going to use this notation tau sigma for the pseudo natural transformation that's corresponding to this lax natural transformation sigma. Okay, so now I want to look at the construction of the reflector, the thing I want the reflector to look like. And that's going to be as follows. So I'm going to take left Kahn extensions of tau sigma along iota. And I'm going to denote that by sigma bar A. Now the problem is this collection of sigma bar A's, we don't necessarily know that these form a natural transformation or a pseudo natural transformation. Another thing we know by Kahn extensions what that looks like. So that is this co-limit formula, which I'm going to refer to later. But what I really want first is to look at conditions when this sigma bar is a pseudo natural transformation. And then by universal properties of Kahn extensions, it's not too difficult to see that that indeed forms the reflector. So yeah, I'm going to look at some sets of conditions for when this is indeed a pseudo-natural transformation. The first one, I'm going to fix a class of categories, phi1, and then I'm going to look at all the categories such that every I shaped diagram has a co-cone for every I in phi1, and I'm going to call it phi2. And then I'm going to assume some conditions on the functors h and g. So first on the functor h, in this version, I'm going to look at the situation where HA is a discrete category. And then I'm also going to assume that H preserves some limits. So I wanted to preserve pullbacks, and I wanted to preserve limits of this shape where I is in phi1. And with this plus notation, I mean to freely add an initial object to this category. So those are conditions on the functor H. I also want to put some conditions on the functor G, namely that GA has some co-limits, namely the ones in phi2, and that GF preserves those. And then in this case, the construction I described above is indeed a pseudo-natural transformation. And yeah, that gives us then the reflector. So this is a reflective subcategory. So yeah, I had some other variations of this that are a bit more general. So the differences are in blue, and then we have some other versions. Then we can also do things when HA isn't a discrete category. But yeah, these are a bit more difficult to check, but we're also going to use those. But I'm not going to say a lot more about what that is. So then we can say something about the co-limits in the category of pseudo-natural transformation. So we already had some results for the lax ones, but now we can also look at the pseudo ones by using this reflector. So basically, when we know that co-limits exist in the lax version, then we can just reflect those back to the pseudo ones, and then we get the co-limits. So that's with this bar operation. And then for some shapes, we also have that we don't even need this bar operation. So yeah, that follows from the previous result. Okay, so what does that then mean for our measures? So okay, I'm going to fix a measurable space, and I'm going to use these functors f, s, and g, which I described before. I'm going to look at this set or collection, I guess, of categories, namely just this one category with two elements, the discrete category of two elements. And then it's not too difficult to show that FS preserves pullbacks, and that this GA has co-limits, certain co-limits, and GF preserves those. So then we can apply the previous results to say that the pseudo-natural transformations are reflective in the lax ones, and we could identify those with measures, right? So then we can say something about suprema or co-limits of measures, and we get exactly the result I mentioned in the introduction, that for directed collections it's pointwise, but then for collections that aren't directed, we need to apply this bar operation. So yeah, taking the pointwise version and then applying this bar operation, and this bar operation immediately follows from this co-limit formula of left-Kahn extensions. So yeah, then that sort of categorically motivates why this is working in measure theory. Yeah, then we can also say, again, by that previous results, the second version of that measures are reflective in outer measures. Because yeah, these are the pseudo ones, these are the sigma lax ones, and then the previous results gives us that this is a reflective subcategory. So yeah, to summarize again, we had this bar construction that sometimes gave us a reflector. And if we applied that to measures, we had that measures were reflective in outer measures. And this bar operation using this formula of Kahn extensions gave us this formula that is, so this formula is well known in measure theory, but now it follows then from the Kahn extension formulas. Okay, then for the last part, where I actually am going to talk about the Carathéodory extension theorem. I'm going to say something about extensions of transformations. So I'm going to fix three functors, f, g, h, and I'm going to look at a Lax natural transformation sigma and a kappa, and I want to extend that to a Lax transformation from h to g in a universal way. Again, for the Lax ones, things are a bit easier. So if we assume, from now on, I'm going to assume that all categories are small. I'm going to assume that G is co-complete, so it's a pre-order, and that GF preserves all co-limits for all the F's in sigma. And then by the previous part, we know that the co-limits are calculated pointwise, and therefore they're all preserved. And then by a lattice version or a poset version of an adjoint functor theorem, we know that this has a right adjoint. So yeah, that gives us the right Kahn extension on the Lax level, at least. So we can apply that to our measures. So I'm going to fix a pre-measurable space. So this is an algebra, not a sigma algebra B. And then I have this FB and F sigma B. And because B is a subset of sigma B, we have this inclusion transformation kappa. And then by applying this result, this one, that immediately translates to saying that this inclusion has a right adjoint. So that gives us an extension of outer measures and outer pre-measures. And in this case, we can even say more that we have this equality. So yeah, because that's not always necessarily the case by just Kahn extensions, we don't always have that. The restriction of the extension is equal to the original thing, but in this case, that is the case. So that was all for the Lax transformations, but we were interested in measures, and those corresponded to pseudo natural transformations. So we want to lift our Lax extensions to pseudo extensions. And to do that, we're going to use this adjoint lifting theorem. So yeah, we always have this 2-cell that always exists. And in the case that this is an isomorphism, we can lift the right adjoints on the Lax level to the right adjoints here. Anyway, yeah, that then right adjoints commute and left adjoints commute. So yeah, this follows from this adjoint lifting theorem. So then we're going to apply that to the measures again. Yeah, we know that the right adjoint on this level exists. Then we can show that this alpha is indeed an isomorphism. So then we can lift the right adjoint to this level. Proving that this alpha is an isomorphism does require some measure theory. So it's not that all the measure theory is completely gone and that it all disappeared and everything is purely categorical. So to prove that there is some measure theory required, but it is true. So we can lift it to a right adjoint on this level. And that finally then immediately says that pre-measures can be extended to measures in the sense of the Carathéodory extension theorem. So yeah, to summarize, we could represent measures and outer measures by transformations. We could reflect those sometimes in the case of measures that all worked fine. And we give some conditions for when that is the case. And then under certain conditions, we can extend lax transformations, and under even more conditions, we can extend further natural transformations, which then apply to measures, gave us the Carathéodory extension theorem. And that, yeah, that's the end.
Thanks for good. Are there any questions for Ruben? So we have a question from an in-person participant, David.
Hi, Ruben. Great talk.
Hi.
I was wondering if you can use this framework to prove things like representation theorems, like Ries's representation. Not Ries's representation theorem, but similar ones in analysis. Is there any work being done on things like that?
So do you mean like linear functionals correspond to measures under conditions? Yeah, so that's definitely sort of what's happening in the background in the first part. Yeah, in these kind of statements, that is definitely sort of what is happening. I don't want to say that one of the results implies the other one, but they're, yes, definitely very connected, and yeah, sort of the same ideas going on in the background. Yeah, I don't know if that really answers your question, but yeah.
Yeah, all right. I'd love to see just more categorical proofs of analysis theorems. I think that's really cool.
Yeah, get on that.
All right. Thank you.
Yeah, thanks.
Are there any other questions for Ruben? Anyone? All right, well, if that's all, let's thank Ruben again. And I'm going to stop the recording.